compute delta y, compute dy for the given values of x and dx equals delta x. And then we can look at a word problem. So we know that delta y is f of x plus dx minus f of x. This is page 255. So this is definitely 2 minus 0.4. So this will be f of 1.6 minus f of 2. Now I plug it in. 2 times 1.6 minus 1.6 squared minus 4 plus 4. So I have, when I distribute, when I put in 2, it's 4 minus 4, and I have to distribute -1. So these two go away. So this is 3.2 minus 1.6 squared. And this is the exact. Yes? Yes? Any questions? Any questions? I got 0.64. This is the exact. So the exact change in the function y for a small change in x of -0.4, the exact change, delta y, is 0.64. Any questions? Please ask if you have anything. I just plugged in 1.6 in the function, and I plugged in 2. And at the end of the day, I got this. Is that okay? But now we want to find dy, which by definition is f of x dx, f prime of x dx. So I have to find f prime, which is very good. And I have to plug in 2. So 2 minus 2 times 2 times dx, which is -0.4. For a -0.4, delta y and dy should be very close. So let's see. 2 minus 4 is -2. Yes. So negative, right? -2.8. Any questions on this? Any questions? Any questions?
Can we do an own?
Sure. Would you like to choose? Please do.
You choose. You choose the best one.
From 11 through 22. Yes.
Before the line says for f prime, did you get 2 minus 2x, right?
Yes. F prime, 2 minus 2x. And when I plug in 2, I have 2 minus 2 times 2 times -0.4. Is that okay? Yes. We were asked to find delta y and dy.
Okay, and then so there's supposed to be an approximate value to the point. The 0.64 is supposed to approximate the 0.8.
So 0.8 approximates 0.64.
Okay.
Because delta x was -0.4. Yes, this, I suppose, this is the exact. Using the derivative, we are getting 0.8. So we are a 0.16 away. Not as good as an approximation as we had on the other functions. Yes. Okay, from 11 through 22. Please choose. 11 through 14 is only asking us to find the differential of the function, which is very important. So let's do one example like that. let's say 14. We are given y equals e raised to tangent pi t. Although it appears to be a function raised to a function, it's not. It's a constant raised to a function. So we're asked to find the differential of y. What do I have to write? What is the formula for the differential of y?
F prime of x dx.
Thank you very much. So then for this function, what will be f prime?
E tangent.
E tangent pi.
E raised to tangent pi t, very good, times the inner function prime, which is secant squared pi t times the inner function prime.
Pi.
Thank you. Times
1. Oh, what the?
times dx. This is the differential of y. And you will see where is this used in chapter 5. So all this piece was f prime of x times dx. Should we choose another?
Yes.
Yeah.
Okay. Let's take a look at 17. With numbers or without numbers? I mean, with numbers is basically reaching both. So we have y equals the square root of 3 plus x squared. We are told that x is 1 and dx equals negative 0.1. They want us to find dy and also evaluate it. So this is just one step more.
F prime times dx.
Very good, awesome.
Or, yes. And then F prime would be 2x. No, 1 over 2x. Or no, I'm including it.
We have to remember, we have to commit to memory the derivative of the square root of a function. We have to try that. So the derivative of a square root of a function is 1 over 2 the square root times the inner function prime. And we will simplify. So dy equals x over the square root of x squared plus 3 dx. This is major in chapter 5. Major topic of chapter 5 when we are going to integrate. Okay, so now we are also asked to plug these numbers in. That's fine. So it's 1 over the square root of 1 plus 3 is 4, and times negative 0.1. So this is negative 0.1 divided by 2, or 1 over 20. Did we get the idea about the differentials and the exact difference in y and the change in x? Do we need more? Yes?
Can we do number 22 and then also
Yes.
the second part where we sketch the diagram?
Oh yeah, the diagram is the one that we sketched together at the beginning.
Yeah, we were- yeah.
This was the
Yeah,
diagram.
better picture.
This is the diagram in which you show the dx and the y. Is there a particular problem that you would like to?
22.
Is it on the checklist? Very good. Okay, so we have to compute delta y and dy for the given values of x and the dx. And then sketch a diagram like figure 5 showing the line segments with length dx, dy, and d. Very good. So here's the graph. The graph of e to the x crosses at 0, 1. The point has x coordinate 0. So this is where I have to draw the tangent. So tangent at x equals 0. I have to picture delta x. So if this is 1, this will be 0.5. I should have used a bigger unit. So yeah, I have to use a bigger unit. It's going to be difficult to see. Okay. Let me know if I need to redraw. So this is the delta y. This is the delta x dx. And this the right triangle. This piece is dy. Using the tangent. Yes?
Will you ask us to draw that on the test?
Not necessarily. But you only, so here's what we show. We have x equals 0. We have a positive delta x, which is 0.5. So this distance is definitely from this point till this point, right? The change in y is the exact change in the function. And then the right triangle is always has the base dx or delta x, and it always finishes with a tangent.
Yeah, there's just a lot going on.
So this is the right triangle, which has the y, the rise, which is dy. That's what I said. I should have used the bigger unit.
You could always do what you did before and just draw a little square and then draw it.
Yes,
Zoom in.
yes, a zoom in. Very good. Okay,
Yeah.
is this idea clear now? Do we need more examples, or are we okay with this? Everything okay?
So are we comparing the values?
I'm sorry?
So are we comparing the values like we did for?
Oh, can you determine that and just put in the values?
That way.
Is that okay?
Yeah.
I mean, all we have to do is just write f prime of x. So this is dy, f prime of x dx. So dy will be e to the x times dx. So you plug in 0 and you get 1. And this is 0.5. So this is 0.5. And then for exact delta y, you have to find e raised to 0.5 because it's 0 plus 0.5 minus e raised to 0. So whatever this is, minus 1. I have to use the calculator for this. So e raised to 0.5 is the square root of e. So the square root of e
0.64872.27.
minus 1, right?
That is after minus 1.
Okay.
I'm sorry, I just gave you the answer.
No, that's fine. So I'll copy it. What is it?
0.6487.
So now we're comparing the exact with a 0.6487. So, any questions? Any questions? I hope that this is not on the checklist. Good.
It wasn't.
If it is, it is. I'm not going to change it. Okay, so back to page 255. Problem 35. This is what the procedure that we just looked at is used for. So let's read the problem together. The circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5 centimeters. Use differentials to estimate the maximum error in the calculated surface area. And what is the relative error? We don't know any of this yet. right? We're going to talk about it. Use differentials in part B to estimate the maximum error in the calculated volume. And what is the relative error? Okay. So first, some preliminaries before we read the problem one more time and write down the information, okay? So the volume of a sphere so it's 4 pi over 3 r cubed. 4 pi r cubed over 3. That's the volume of a sphere. What is the surface of a sphere? Easy to remember. The derivative of this. Can anyone give us the derivative of this? That's it. So the volume is 4 pi over 3 r cubed, and the sphere, the surface of the sphere is 4 pi r squared. So now we can read the problem one more time. The circumference of a sphere, C, which is 2 pi r, the circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5. At this point, I have to stop and think, what does 84 mean?
Equal to 2 pi r.
What does 84 mean in the context of what we've just been doing? Correct. What does 0.5 mean?
Delta.
Yes. Very good. So that is x. The minor change, possible error, is 0.5. So far, so good? Okay. Use differentials to estimate the maximum area in the calculated surface area. So the circumference was measured to be 84, I'm sorry. So this is C, and this is DC. Okay? This is C, and this is DC. Because the measurement is given for the circumference. So we have to use the notation, unless I change this into X, but I would like to use C. So the circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5. Perfect. So now we are asked to use in part A, use differentials to estimate the maximum error in the calculated surface area. So an error in the circumference will trigger an error in the area. How do I denote the error? Careful, let's go back. Do I go that far? Okay. Exactly. Exactly. So this is the error. Remember what I said from when I said, okay, let's see how we memorize this or remember this. The function applied to x plus an error in x, if you want, equals the function plus an error in y. So the function of x plus a little bit of x, some change in x, equals the function plus some little change in y. So I am told to find the error in the area, which will be the area prime times
dx.
In this case is dr. Very good, awesome. Exactly, because now the area depends on the area. I should use S. I don't want to confuse you. I need to use the same letters. So the area of a sphere. Okay. So what is the area function of? Just the radius. right? So if this were f of x, then I would have written dy equals f prime of x dx. But it's area over radius. So that's why it has to be a prime times dr, because there is no other variable in the surface area but the radius. Good. So let's look at a prime, which is 8 pi r. So then the error in the area will be 8 pi r times dr. Now, I don't have this, and I don't have this. Okay, I have to come back to the information I have. So this is 2 pi r. From here, I will be able to find r, which is 84 over 2 pi. From here, bless you. So this is the error in the circumference. So now I have to differentiate the circumference. So dc equals 2 pi. So now from here I have to, somehow I have to find the dr. So when I differentiate both sides here, I get dc equals 2 pi times dr. I will solve for dr, dividing both sides by 2 pi. So dr equals dc over 2 pi. And this is my dc, and this is my 2 pi. I think I should do this one more time. Okay, so let me start from scratch so you're not confused by that, and I'll come back to it. So in order to find the error in the area, I have to write a prime times dr. Why dr? Because the area only depends on radius. Okay, so when I differentiate this function with respect to r, this will become a prime is 8 pi r. So I go back, I replace 8 pi r times dr. I will be done the moment I determine this and I determine this. These two pieces are not given to us. So then, how do I determine them? Well, I will have to differentiate this to find dc as being 2 pi of c is a function of r only. 2 pi times dr. That's a differential of c. So from here, I will find dr, dividing both sides by 2 pi. Because this is given to us. dc is given as 0.5. So I have this piece. Now the question is, how do I determine this? Not a problem, because I'm given c. c is 84, 2 pi, and I can determine r to determine this piece. So 84 equals 2 pi times r. So from here, r equals 84 over 2 pi. So now I have this also. And that's where I was. dA, the error in A, for a minor error in the circumference, equals 8 pi r times dA, 8 pi r times dr. So now dr is 0.5 over 2 pi, and r is 84 over 2 pi. And that's the end of it. 8 pi times 84 over 2 pi times 0.5 over 2 pi. This will give us the exact or the approximation. Of course. So this will be, but that's what it says. Use differentials to estimate. So it's an estimate. The maximum area in the calculated surface area. So I will simplify before I do anything. So 2 and 2, and there is a 2 here, so that's 4 divided by 4. These two go away. So then I will have 2 times 1/2 is 1. So the whole thing is 84 over pi. So I will divide 84 by pi. 84 divided by pi. And I get 26.738. 26.738 measurement unit. Yes. So when the circumference is 84 and there is a minor error of 0.5 in the circumference, that error triggers an estimated error of 26.738 squared centimeters. Any questions? Any questions? So when the circumference is exactly 84, but there is an error of 0.5 centimeters, that error will trigger an error in the measure of this circumference, of the area, of the surface area, of 26.738 squared centimeters. It doesn't matter if it's positive or negative.
So it's the same.
Yes, yes, yes.
So what's the relative error?
Very good. That's the next step. I just waiting for you to say, okay, relative error. The relative error has no measurement unit. The relative error is the error over the area. The error in the area over the area. So this is dA over A. So let's see what is the easiest way to write this. dA is 8 pi r dr, and A is 4 pi r squared.
We already knew what 8 pi r dr is 26.738, isn't it?
Yes, but I would like to see the ratio. But yes, we can simply divide this by the area, plugging in the radius. Where is my radius? Where is my radius is here. 84 divided by 2 pi. So I will have 4 pi and replace r squared by 84 times 2 pi. I just wanted to show how we calculate the, but then we can go to the numbers. Because here's what happens. Pi and pi, 4, 2, r and r. This was the point I was making. Twice dr over r. So what does this mean? The relative error in the area produced by a minor error in the circumference of 0.5 centimeters is twice the relative error created by the same thing in what? In the radius. So that's why I wanted to show you the formulas before plugging in numbers. So the relative error in the area triggered by an error of 0.5 centimeters in the circumference is twice as much as the relative error in the radius, triggered by the same 0.5 in circumference. So now if we want to determine it, we can simply go back and replace the top, which we have determined a minute ago, which was this, 26.738, and divided by, I have 4, I have pi, and I have r squared. What was r? Yeah, the whole thing. 84 over 2 pi squared. Or you just use this, which is dr. 0.5 over 2 pi, 2 times 0.5 over 2 pi. That's even easier. divided by the radius. It's up to you. So one more time, here's what I did. Assuming I did not simplify, I already had the A, which was 26.738. But now the denominator is 4 pi times the radius squared. So the radius is 84 over 2 pi. So now we have to calculate this. So dA over A equals 26.738 divided by 4 pi times 84 divided by 4 pi squared. So this will become 26.738 times pi over 84. So let's see what is the relative error. There is no measurement unit because this is in centimeters squared and this is in centimeters squared. Relative error does not have measurement unit. So I multiply now this by pi and I divide by 84. Okay. I got 1. So it was 26 point, I multiplied by pi, yes, and I divided by 4, 84. Oh, of course. Sorry about that. 0.01194. 84 squared. So 84 squared divided by 4 pi squared made no sense. So that's why I was looking to see what, okay. So 4 pi, 84 squared. So what is the relative error? The relative error in the surface area is 0.00, which means 1.19%. So 1.91% of the area. Part B. Use differentials to estimate the maximum error in the calculated volume. And then what is, yes, please, Paul?
Yeah, I was just saying for the relative area, since we had 2 times dr, I mean, 2 times
yes,
dr over r,
yes, yes. So dr was this,
yeah.
But then I had to determine r.
Well, we had r from before.
We had 84 over 2 pi.
Yeah, so when I did
That's fine.
Over the
so you had the top as being 0.5 over 2 pi,
yep.
And then you flipped that and you get 0.5. Okay, so you have 1 over 84. It's fine.
Yes.
Fine. You got the same answer.
Sure.
Yes, of course. What I'm more interested in is this. This is more useful than the actual number. To see that this particular error in the circumference of 0.5 centimeters trigger is basically twice as much as the error in the relative error in the radius. Okay, so we repeat the same process for volume. So I messed up my numbers here. 9, 9, 10, and this is 11. Okay, so please tell me what to do for the error in the volume. So let me write the volume one more time. So 4 pi divided by 3 r cubed. So we want to find dV. What? So 4 pi times, just remember, dV is not the same with V prime. dV is V prime times dr. So do not confuse. So when you write dV, you must end with some d something. Okay? Because dV over dr is f prime. So when you are asked to find dy, you have to write f prime dx. Is not clear? So f prime of x is one thing. But when I'm asked to find y, dy, I have to write f prime of x dx. When I'm asked to find dv, I have to write v prime of x dr. I'm not asked to find f prime or v prime. I'm asked to find the differential of v. which is v prime times dr. When I'm asked to find the differential of y, I have to write f prime of x dx. So this is dy over dx. So f prime is dy over dx. So this is not a derivative. So you cannot stop here. If this were v prime, you would have stopped at 4 pi r squared. But this is not a derivative. This is the differential of v, which is v prime times dr. Do we understand the difference between these two? Is that clear? So when I'm asked f prime, I'm asked this ratio. When I'm asked to find dy, I'm asked this product. So when I'm asked dy, I have to find f prime times dx. If I'm asked this, then I'm asked to find this ratio.
So are we always going to use
Let me show the difference before you ask.
radius
Before
as the, like, in respect to?
is the only, because it's the only variable in v. It's the only variable in v.
Oh, okay.
So let me show let me show you the difference. So let's say we have a function which is x cubed plus 2x. Okay? We can be asked to find two different things. One is f prime of x, which is 3x squared plus 2, and I'm done. But if I'm asked to find dy, I have to write 3x squared plus 2 dx. Is this clear? The differential of y has to end with the differential of something of the variable, d of the variable. F prime is just the derivative. The differential, so where does this come from? F prime of x equals dy over dx. If you put this over 1, you cross multiply, and you get dy equals f prime of x dx. And that's what we have here. So coming back, this is correct, but this is incorrect. I have to finish with dr. Is that better? Okay, perfect. So then, let's see what we have and what we don't. So 4 pi is clear. R, we determined it before. What was R? Right here. So this is 84 over 2 pi everything squared. And we also have dr, which is 0.5 over 2 pi. Everything is the same, it's just that it's a different function. It's a different differential. So dv, the differential, the error in dv, the estimated error. Stephen, you had a question I forgot to answer. You had something.
Oh, you did answer.
I did?
Yes.
Okay, sorry. So then I have 4 pi times 84 squared over 4 pi squared times 0.5 over 2 pi. I would like to simplify a little bit. So then I have 84 squared times 0.5 over 2 pi squared. So let's see a 0.5 error in the circumference. How much error in the volume it will trigger? So we have 84 squared times 0.5 and divide everything by 2. Either put parentheses, let's put parentheses, is much better, times pi squared. (178.73) measurement unit. This has a measurement unit, is not the relative or the percent error. So what is it? Very good. So an error of 0.5 in the circumference of the sphere triggers 26 blah 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 centimeters squared error in the surface, and it triggers 178.73 centimeters cubed in error in the volume. So now, of course, we want dv over v as the relative error. So I will copy 4 pi 4 pi r squared dr over the volume, which is 4 pi over 3 r cubed. For the same purpose, because I'm more interested to see what is the relationship. So 4 pi with 4 pi will go away. An r squared with an r squared from the bottom, I flip, and look what this is. So the relative error in the volume is 3 times as much the relative error in the radius. So if we have this from last time, then we can directly find it. So what was R? R was 84 over 2 pi, and no, dr first. Dr first, sorry. R is 24, and then 0.5 over 2 pi. Yes. So 2 pi and with 2 pi go away. So 1.5 over 84. And we'll see the percentage. Previously it was 1.11 in the area, surface area. So this time is 1.5 divided by 84. So it's 1.8 almost. So this is 0.01785, which is approximately 1.8%. Did we get the same thing? Okay. Yes.
Question.
Yes.
So on dv, you have 84 squared over 4 pi squared?
Yes. So dr was 84 over 2 pi.
In the blue or purple, I don't know what color it is. Colorblind.
I'm sorry, dr. Oh, in purple. Okay. Here or here?
Yeah, on that one.
Okay.
Yeah, 4 pi squared. Where did that 4 pi squared come from on the denominator?
So we had r squared. So this one?
Yeah.
So we had this. So this was 84 over 2 pi squared. So 84 squared over 4 pi squared. And then 0.5 divided by 2 pi. So 4 with 4 went away. This pi with this pi went away. So I have 84 squared times 0.5 divided by 2 times pi squared. Was that the question or not?
I guess I'm still confused how the 4 is coming in.
2 squared.
Oh. Okay. Got it.
You mean this one in the denominator?
Yeah.
Okay.
Zinga, got it.
That's okay. Okay, I know I only have a few minutes left, like 9 minutes. So let's look at last topic here. Yes. This is called linear approximation. No, same section, same section. I did the course stop first, and this is easier. Okay, so let's look at this function again. And we have a point. And this time is, yes, of course, a f of a. I am going to draw the tangent line. Can anyone give us the slope of the tangent line at P? Yes?
Okay.
Very good, awesome. So now I would like you to give me the equation of the line y minus y1 equals the slope times x minus x1. I would like you to use the point slope form to give the equation of the tangent line at P. So please tell me what to write. I would like to determine the equation of the line that is the tangent at P. What do I put here?
A.
What do I put here? What do I put here? Perfect. So then, y minus f of a equals f prime of a times x minus a. Of course, I can, you're way ahead of me. That's perfect. So this is indeed
It's the same thing.
very good, very good. Exactly, it is. Okay, so this is the equation of the line, equation of the tangent line. And now I'm going to say something, and you'll tell me whether you agree with it. F of x is approximately f of a plus f prime of a times x minus a near a. Near P, but you know what I mean, near A. So does this resemble anything that we've been talking about?
Everything.
Thank you.
It's the super important, super F.
Slightly different, however. Yes, this is the function, but it's evaluated, and this is x minus a, but obviously it has to be near a, which means dx. Right. So this is nothing else but called the linear approximation of f of x near a. This is exactly what we did with the cost function. If you remember, I said if we change the number of units we manufacture per day, tiny change, then I can still use the same slope, the same tangent line, and this is what it says. So also there is also something called the linearization, which is the same thing without the approximation, and it's denoted by L. So exactly the same thing. L of x without the approximation, equal symbol, f of a plus f prime of a times x minus a is the linearization of f of x near a. In other words, near a, if I use the function to determine something, values, whatever, or I use the tangent, I get very similar, I get close results. But only near A, not here. That's not near A. Not here. That's not near A. But near A, if I use the actual function or f prime of x dx, I get very close. And that's called the linearization. After this, beyond this, there are nothing else new. I only need 5 minutes to show you 3 functions from 311. And that's it. That's the end of chapter 3. But I would like to find the linearization, one problem, and we'll stop. Let's say problem 3. Same page at the top, 255. So f of x equals the square root of x, and a is 4. Find the linearization, L of x. In other words, find the straight line that you could use to evaluate this function instead of the function itself near what?
4.
Near 4. That's all it means. So I have f of 4 plus f prime of 4 times x minus 4.
2 plus.
I have to find f prime of x first. So f prime of x to the square root of x. So this is indeed 2. How much is this?
1/4.
Exactly. So remember, it has to be a line. It has to be a function. It's L of x. It's the function that may replace the function itself. It's a line that may replace the function itself if you are tired of using the function and you don't care if you have a minor error. You can use the line. So L of x equals 2 plus 1/4 x minus 4. It will always be a line that approximates the function near that point. But when we mean near, we mean near. So one more time, if you use the function to evaluate or use the tangent at that point, you can use this. This is a linearization. Of course, I'm going to simplify. 1/4 x minus 1 plus 2 is plus 1. This is the line that approximates the square root of x near a. If you move to 3, it's not going to be the same line. If you move to 2, it's not going to be the same line. It's going to be a different line because the slope will be different.
At 4.
But near 4, if you want to evaluate this function at 3.8, you can do it with this. If you want to evaluate this function at 4.1, at 4.2, 4.3, you can use this. But if you want to evaluate it at 5, you have to create a new function with f prime of 5 and f of 5 and x minus 5. Okay? So this will give you a very good approximation. It's not going to be exact. Because remember, 200 and 201. Any questions? Any function can be replaced near a point, at any point, by a line using the method of linearization. Any questions?